Hello everyone, my name is Charlie Esmarzan from Don Mariano Marcos Memorial State University, Philippines. Today I will present my study titled MorphoNet Mugil, a deep learning based application for automated morphometric measurement of Mugil cephalus. Accurate morphometric measurement of Mugil cephalus is very important in aquaculture, particularly for monitoring growth, evaluating health condition, and assessing production performance. These measurements are commonly used by researchers and fish farmers to ensure proper development and to improve management practices. However, the traditional method of measuring fish morphometrics using rulers or calipers is time-consuming and labor-intensive, especially when a large number of samples need to be measured. In addition, manual measurement is prone to human error, which may affect the reliability and consistency of the collected data. The increasing demand for efficient aquaculture production requires measurement methods that are fast, reliable, and easy to perform, especially when dealing with large number of fish samples. Traditional approaches are no longer practical in many real-world aquaculture environments. Fortunately, recent advances in deep learning and computer vision make it possible to automatically detect anatomical landmarks and compute precise morphometric measurements directly from images. These technologies allow the development of intelligent systems that can reduce human effort while improving accuracy and consistency. Because of these limitations in manual measurement and the opportunities provided by deep learning and computer vision, the next step is to develop an automated and practical solution. The main objective of this research is to develop a responsive web application that can automatically recognize and quantify the morphological attributes of Mughal The system is designed to capture fish images using a smartphone, detect important anatomical landmarks using deep learning, and compute morphometric measurements automatically. In this study, a total of 2,824 Mugelcephalus fish samples were collected. The samples came from two main sources to ensure diversity in size, shape, and condition. First, fish were obtained from the fish ponds at the College of Fisheries of Don Mariano Marcos Memorial State University South La Union campus. Second, additional samples were collected from local wet markets located in Agoo, Santo Tomas, Caba, and Aringay in La Union, Philippines. After collecting the fish samples, the next step of the study is to define the morphometric measurements that will be used for analysis and model training. In this research, I used the Trust Network morphometric method, which is commonly applied in fish morphology studies because it provides a detailed description of body shape. Using this method, a total of 34 morphometric measurements were defined based on distances between anatomical landmarks across the fish body. These measurements allow us to capture variations in length, height, and body structure more accurately compared to simple length measurements. To obtain these measurements, I manually annotated the images using the CVAT annotation tool, where 24 anatomical landmarks were placed on each fish image. These landmarks serve as reference points that allow the system to automatically compute the required morphometric distances. The annotated landmarks were then used as ground truth data for training the deep learning model to perform automatic landmark detection and measurement. In the data preparation stage, all images were pre-processed by resizing and applying augmentation techniques in order to improve model robustness and prevent overfitting. The dataset was then divided into 70% for training, 15% for validation, and 15% for testing to ensure reliable performance evaluation. For modeling stage, several deep learning architectures were evaluated, including ResNet 50, CovNext, NASNet Mobile, EfficientNet V2, and MobileNet V3. These models were selected because they represent different levels of complexity and efficiency, allowing us to compare performance in terms of accuracy and computational cost. For evaluation, we use the object key point similarity, which measures how accurately the predicted landmarks match the ground truth annotations, and mean absolute error, which measures the difference between the predicted and actual morphometric distances. After the training, the different learning models, we evaluated the performance using training and validation accuracy to analyze how well the models learned the landmark detection task. The figure on the left shows the training accuracy, where all models gradually improved as the number of epochs increased. The figure on the right shows the validation accuracy, which is more important because it represents the model's ability to generalize to unseen data. Among the evaluated models, Cognex and EfficientNet V2 showed more stable and consistent validation performance, indicating better generalization compared to other architectures. These results suggest that deeper and more modern architectures can provide more reliable landmark detection for morphometric measurement. After analyzing the training and validation performance, I further evaluated the models using quantitative metrics for key point detection and morphometric measurement. This table shows the comparison of the five deep learning architectures using the OKS at zero point 0.5 and zero point 0.75 thresholds, together with the mean absolute error, which represents the accuracy of the computed morphometric distances. All models achieve high OKS values at zero point 0.5, indicating that the predicted landmarks were very close to the ground truth annotations. However, differences can be observed when we consider stricter evaluation and the measurement error. Among the tested architectures, Cognex achieved the best overall performance, obtaining the highest OKS score at zero point 0.5 and the lowest mean absolute error of 3.66. This means that Cognex produced the most accurate landmark detection and the most reliable morphometric measurements. Because of this, Cognex was selected as the final model for the developed morphometric measurement system. After selecting the best performing model, the next step of the study was to deploy the trained network into the responsive web application so that the system can be used in real world aquaculture settings. The application allows users to capture or upload in an image of Mugelcephalus using a smartphone or any web enabled device. The system automatically detects the anatomical landmarks, constructs the trust network, and computes the morphometric measurements in real time. As shown in the interface, the application displays the detected key points, the generated trust network, and the calculated morphometric values. Users can also view previous scans, download the results, and access measurement history through the web interface. In addition to automatic measurement, the developed responsive application also provides several user-friendly features for managing and analyzing the results. As shown in the interface, users can view the history of previous scans where all processed images together with detected landmarks and computed measurements are automatically stored. The system also allows the user to download the results in spreadsheet format, making it easier to use the data for further analysis and research. After deploying the system as a responsive web application, I conducted a real-world performance evaluation to determine how the proposed system performs in practical conditions. For this test, five fish images were captured using a Samsung S23 smartphone, and the measurements obtained from the Morphonet Mugel application were compared with the manual measurements performed by experts. The results show that the proposed system achieved an average mean absolute error of 4.91, while the expert measurements obtained an average error of 3.31. Although the expert measurements were slightly more accurate, the difference is relatively small and still within an acceptable range for morphometric analysis. In terms of speed, the advantage of the proposed system is very clear. The Morphomet Mugil application required only about 5.24 seconds per image, while manual measurement by experts took approximately 17 minutes per sample. This demonstrates that the proposed system can significantly reduce processing time while maintaining reliable accuracy, making it suitable for real-world aquaculture applications. After evaluating the system in real-world testing, I also analyzed how different image capture conditions affect the measurement accuracy. In this experiment, Images were taken under different distances between the camera and the fish, particularly comparing too close capture and normal capture conditions. Results indicate that landmark detection remained functional under normal, bright, and low conditions, as well as when images were captured too close or too far from the subject. However, detection failed under extremely dark conditions, highlighting the importance of adequate lighting for reliable landmark condition. Overall, the results demonstrate that Morphonet Mugil maintains stable performance across varying capture conditions, provided sufficient illumination is available for accurate detection. Based on the conducted experiments and real-world testing, the proposed Morphonet Mugil system demonstrates that automated morphometric measurement using deep learning is both feasible and effective. For aquaculture stakeholders, including hatchery managers, fish breeders, and researchers, the system enables faster growth monitoring, improved stock assessment, and more consistent data collection. This can help support data driven decision making and improve productivity in aquaculture operations. Several improvements can be considered for future work to further enhance the performance and usability of the proposed system. First, future studies may focus on improving image pre-processing by applying adaptive illumination, correction, contrast enhancement, and noise reduction techniques. These methods can help improve landmark detection accuracy, especially under challenging lighting conditions. Second, expanding the dataset, optimizing inference for lower resource devices, extending the framework to support multiple fish species, and integrating automated image quality assessment to enhance reliability in real-world deployment. This concludes my presentation. Thank you very much for your time and attention.